Good afternoon, Nullcon. Thank you for joining. In this presentation, we will be talking about a topic called Android-SigMorph. It's a covert communication technique exploiting Android signing schemes. So in this presentation, if you feel like we are nervous, that's because we are. This is our first time presenting at a security conference, so please pardon us. So before we go into the content, just a quick introduction of who we are. I am Ayan Shah. I am a security researcher who was working with Keysight. I used to do vulnerability research. I like to play with Android, hence the talk. I do a bit of CTFs and I'm a cat lover.
Yeah, thank you guys for attending the talk. And I'm Achut and I am the technical lead for a security group within the Keysight. We call ourselves like application and threat intelligence team, and we day to day we deal with like looking at CVs, reverse engineering them, and playing around with malwares and stuff. And I generally love everything around security. So let's go back to the talk title. So our talk title is titled Android-SigMorph. Let's break down that SigMorph, right? SigMorph means signature morphing, right? So what do we actually mean by that is without breaking the signature of an Android or an APK file, how can we misuse the APK file format specification to allow additional data to be appended, right? And this additional data that is appended can be now, used for good purposes as well as for bad purposes. That is what we'll be looking into. And before we go there, understanding what this Android signatures and all the stuffs, let's look at how traditionally Android apps have been modified. So traditionally, there is something called Android app repackaging, where this is generally a 5-step process where we take an APK, we decompile it first, we then modify the code, maybe the smally code, and then we rebuild it and then sign it with a custom certificate, right? And as soon as we had decompiled the APK, the signing information is lost, and when we sign it with a new custom certificate, as far as the Android ecosystem is considered, that's totally a new app, because it has been signed by a new developer key, right? It's not the same app anymore, it is totally a different app, right? And basically when you do repackaging, a lot of detection signals go everywhere, right? Android themselves do not allow you to install such apps, but they give you an install anyway option. But generally it means that, when you repackage, you run into checks. So what we are trying to achieve here is, without repackaging, can we take an Android APK binary directly, modify it in the hex, right? And then we release it, right? And on this process, we do not want to break the signature at all, right? So before we go deep into how we do that, let's look at the Android signing schemes that are, the history of it, and how it has been exploited in the past, and we'll be presenting our research on V2. Thank you.
So before we go into the signing schemes, just a quick refresher. What happens in signing is that when a developer creates an app, he or she encrypts it with their private key, so that when the app reaches the user, they are able to make sure that the app hasn't been modified in between. Since the talk is about the signing schemes, let's go into them. So in the Android ecosystem, there are 4 different signing schemes that has been introduced. First, we have the V1, which has been there from the beginning of Android. Then we got Android V2 signing scheme in Android 7.0. Then we got V3 in Android 9.0, and recently, a couple of years back, we got the V4 signing scheme. So we will be going a bit depth into most of these signing schemes, like mostly the V1 and V2. So in V1 signing scheme, what essentially happens is it's based on jar signing scheme, which was a open standard for signing jar files. And Android just imported that as their signing scheme for V1. And what happens in V1 is that when we have the APK file and when we sign it with the V1 signing scheme, a particular folder called this meta-inf gets created, and inside the meta-inf there are a few files. The first file that's important is the manifest.mf file, And what that contains is, it will contain the SHA-1 digest of each of the entries that are present in the file. If you see in the first screenshot, you can see the contents. Then we have two different files called cert.sf and cert.rsa. The cert.sf, what it does is, it basically will contain again a SHA-1 digest, but of each of the entries that are in the manifest file. So if you see like the entries of manifest and the cert.sf, like they are kind of similar, but in the cert.sf it just contains the SHA-1 digest of the manifest. So it kind of protects the manifest file itself. Then finally we have the cert.rsa or the DSA file, which is created when the particular cert.sf file is being encrypted with the developer's private key, and the output the signature and the public key to verify is being embedded into the cert.rsa. So that's what it contains. So it's kind of a a chain of protection, or a chain of signature that happens, like one file is protecting the other. Now, one more thing to note is that this cert.sf and this cert.rsa, they come in pair. So there could be more than one pairs of them in the meta-inf, which means is that what that means is that like multiple signers are signing the same APK. So we have more than one pairs, and when the Android ecosystem will be verifying the APK, they would need to verify for all of the signers. Only then it will install. Now let's look at some of the issues that there are in V1. The first issue was kind of because of how this V1 signing scheme was designed. The issue is that the charge signing scheme or the V1 signing scheme, it does not stores the signature of any files that are being added inside the meta-inf folder. So if you remember, the meta-inf folder contains those cert.sf, manifest.sf. So if any extra files are dropped there by the developer, those won't be covered by the signing scheme. So what that means is that any attacker could just take a signed APK, and if there are files inside the meta-inf, they could just replace them. So if the developer, let's say, was loading some files from the meta-inf and loading it into their code, those would get replaced without breaking the signing signature. Now the good thing is that like most of the APKs that are in Play Store, even though some of them have files in meta-inf, if you can see in the screenshot, they also come with the later schemes with them, like V2 and V3, because signing schemes can appear in combinations. So this issue should not be much of a big deal now. Now, another way of thinking about this problem, instead of replacing files, someone could actually add new files inside the APK, and the signing would still be valid. So this kind of serves as a steganography technique without breaking the signature. So we have this V1 signed, and someone could unzip it and just put in the file, and the resultant file will still be verified. I mean, signature will still be preserved. The next issue for V1 that we have is the master key vulnerability, which was introduced which was disclosed quite a while back. Essentially, what the issue was that when we have a V1 signed APK, an attacker could just add a duplicate file, let's say the classes.dex, right, which actually contains the Android source code. An attacker could just add a malicious classes.dex, the red one, over the non-malicious green one, and during the install time, the Android verification, it would since both the malicious and the non-malicious file are of the same name, during the install time, the Android verification, it would just consider the non-malicious file, and it would just still pass the verification. It just ignores the malicious file. But during the runtime, the reverse thing happens. The green one will actually get ignored, and the red or the malicious one will actually get executed. The last issue in V1 that we are aware of is called the Janus vulnerability. Here what happens is that, again, we have a V1 signed APK, and what an attacker can do is just append a malicious DEX on top of the APK file, and in zip, or in v1 signing, what happens is that, or in the zip parsing, what happens is that the APK is being parsed from the bottom. So anything appended at the top in the v1 signing scheme actually gets ignored. So during the verification, since the malicious DEX file, right, it's at the top, that gets ignored, so it passes the verification. But during the runtime, what happens is the Android runtime, it can actually, run both DEX and APK files. So when it gets this resultant file, it will see that the DEX file is at the top. It will see the DEX header and, think of it as as a DEX file, and it will just execute the malicious DEX file. So what that allows one to do is maybe append a DEX file to a system app, which is which usually runs with more privileges, and pass that as an update to your existing system app, and hence the DEX file will run with more privileges.
Yep, and that was all that we had for V1. So that was like in the past, right? That was all the research that was done for V1. Now with V2, what Android introduced was something called a whole file signature. But we'll look at it that it's not actually a whole file, right? And if you read between the lines, it says that protected parts of an APK. So that means there are certain unprotected parts of an APK, and being the hackers or researchers that we are interested in those parts, right? And if we look at an APK file is basically a jar file. A jar file is basically a zip file, right? And if you look at a zip file structure, it mainly consists of 3 different blocks: the end of central directory, and then the central directory, and then the contents of the zip entries. And why I put it in the reverse order is that for zip, it's like a reverse readable file. So the format specifies that it needs to be start reading from the end of the file. We start from the end of central directory, get an offset to the central directory, and then get an offset to the files inside the contents of the zip entry. Now this is before signing. Now once after we sign an APK right now with V1, V2 or V3, what Android does, it adds a new block called APK signing block, just before the central directory. And if you look at the image, the red ones are basically the protected ones, and some parts of this APK signing blocks are unprotected, right? And that is what we will be trying to deep digger in our talk. So if we zoom up further into this APK signing block, it basically has a structure where we have the APK sig block for T2 magic mentioned, then the length, and then again the length at the very beginning. And it makes sure that the length needs to be in, same. What is between these lengths are the interesting bits of blocks that get added when an Android signs. And we will see here like lot of tools, processes adds their own kind of blocks in there to detect something, right, which we can mess with. So let's look at this kind of blocks in more details. There are certain mandatory blocks here that needs to be present. So we'll start off with those. We will see how V2 signing works, and then we'll cover the other blocks that are there and what can allow us the freedom to, move stuff around or change stuff around here.
So let's first take a look at the one of the first mandatory block, which is the V2 block, which actually contains the V2 signature inside the APK signing block. So if you look at the structure, like what happens is a zip has 3 entries, right? The blue, green, and the purple one. So those are the protected parts which needs to be protected. What the V2 parsing scheme does is it will take those 3 parts out and concatenate them, and then break them into individual digests of 1 MB each, and those further those small digests will be calculated into a bigger digest. So this particular digest is actually protecting the 3 segments of the APK or the zip. And if you look at the structure on the left, that particular digest is being inserted into the V2 block, the digest section, and along with it what goes is the public certificate of the private key that was used to do this signing. So these are the 2 parts parts which are protected in the APK signing block. Also along with it comes the signatures to be able to verify the V2 signing, the V2 signing letter, and along with it again the public the public key appears just for verification purposes. Now let's take a look quickly at the V3 block. Again, V3 block is kind of similar to V2 block, at least from our talk perspective. It's not much different. It has a particular ID which is different than V2. The only thing that V3 introduces is this concept called proof of rotation, which essentially allows app developers to switch between old and new certificates seamlessly. That's it. Now, since we're done with two of the important V2 and V3 blocks, let's now try to look at some of the more obscure or optional kind of blocks. First one that we have in our list is called the verity padding block, which has this particular ID, and it's nothing. It's just used to pad the signing block that we saw to a multiple of 4096 bytes. Now, why that is done is because having a fixed size has advantages in input-output operation speeds. One more point about this verity padding block that we saw in the Android source code was that let's say if you were to modify an APK which has this verity padding block, you need to make sure that the resultant APK also needs to comply to that rule of being a multiple of 4096 bytes. So you need to pad the resultant APK if the verity padding block is already present. Next on the list is the source stamp block. It's basically kind of version control information. So metadata about the date and time of the build, or the version of the build tools used. So essentially, it contains information about the source code that was used to compile the APK. So it kind of identifies that. Now, we tried modifying this source stamp block, and there is actually a separate verification that happens for the source stamp block if we use something called APK signer. And when we modified this particular block in the APK, we saw that verification fails. That is because this particular block, right, this particular source stamp block has the the SHA-1 digest, or SHA-256 digest of this block is actually stored inside the APK in the file called stamp cert SHA-256, if you can see it in the screenshot. And since the APK file itself is protected, we can't really change that part to be able to verify the verification of the source stamp block. Again, this source stamp block verification is different from the actual APK verification. Now, the next interesting block that we found was something called the Google Play frosting. Now, this was introduced back in 2018 by Google to prove that an APK has originated from a Google Play Store. That makes sense, right? Because there are a lot of app stores, or people often sideload apps. So there needs to be a way to actually say if a APK has came from a Google Play Store or not. So that's what it does. This particular block, it's protobuf encoded, and the block itself is signed by Google's private key to provide that authenticity. Now, there are some tools out there, open source tools out there, which actually verifies this Google Play frosting. One such tool is called APK Verifier by Avast, which we tried to run on a Facebook APK, and if you see on the first run, the frosting gets verified because it's an unmodified APK downloaded from a Play Store. And we tried changing a single byte of the Google Play frosting and see what happens. And as we expected, the validation gets failed. One more like experiment that we try to do is that let's say as a malware author, right, I got curious that can we just copy the frosting, let's say from Facebook APK, and put it in my malware code, and would that be able to somehow fool the tools out there which passes this block? The answer is no. You can see like it's giving a frosting APK file digest mismatch. Now, why that happens is that the APK's digest, right, itself is stored inside this block, and that block gets encrypted by the Google's private key. So since we transferred the block from the Facebook APK to a malware APK, obviously the malware is a different file, so the SHA-256 would have needed to be changed. So we can't really change that, and that's why it fails at the parsing part.
Yeah, the next type of block that we saw was the dependency info block. Basically, this gets added not by Android or the APK signer, but by the Gradle, right? So, and as soon as we hit build in Android, Gradle takes over and it tries to do something, right? So what it does in the process of the building is that it adds a block which contains like the SDK dependencies and all the stuffs as part of the APK file format. And where this is used is when Google Play analyzes the apps that are there that we have uploaded them, and they gives us some recommendations based on the SDKs that we have imported, right? So we can change this because it's not encrypted as much, but there is not much malicious use case to it. We can definitely strip it out so that there is no checks performed by the Play console, but there is not much malicious use cases here. And the other interesting block that we found was a zero block ID. Basically, a lot of zeros were there, and every time it was like 0 multiplied by 4084 times. The unique thing about this is we only found this in Facebook or Instagram related APKs, and maybe there is a Easter egg to it. If you look at the hex code of the ID and we look at the Facebook blue, the hex code matches, right? So maybe a Easter egg from Facebook. I still don't know the purpose of this. When we have a verity padding block, why did we need this? The other kind of block that we saw was an APK channel block ID. Mostly Chinese APKs had this, and this were basically used to track the APK distribution, right? So if I'm distributing my app from, let's say, Samsung Play Store or Google Play Store or Xiaomi's, then, in order to track those, they put those kind of stuff as a JSON in the APK. And we can always change this because it's just a single JSON, right? So let's look at a quick demo, or where we will try to change in the hex of a APK and still make sure that the verification holds. And we'll use this APK in our later part of the second demo, where we'll be demonstrating code bombs.
So let's actually try to modify an APK. Okay. So here, if you see, we have this Facebook original APK, and if we just quickly try to look at its MD5 sum just for reference, it's this one, and let's try to try to see the verification status of this original APK. I'm guessing like it should pass because it's just the original APK. Right, so if you see like APK of a signer is saying it's properly verified. Now let's do one thing. Let's make a copy of this Facebook APK into this modified .apk, right? And let's try to open this in a hex editor. Let's try to find those obscure blocks that we talked about. Let's try to find the verity padding block, which has this particular ID, and this is the value of the verity padding block. And let's see what happens if we change parts of this signed APK, especially in this verity padding block. Let's put something, maybe hi Nullcon, this is malicious data. So we have saved it, and just for reference, if we look at the MD5 sum of this modified APK, it's different, right? So it's F70 and this one is F50. Let's try to see if the APK still verifies. So modified APK. Okay, so as you can see, even after like changing parts of this optional block or like this verity padding block, the APK still verifies, which is actually like which I wanted to show. Now, why exactly this happens is that So why exactly this happens is that we had the APK signing block, right? And the APK signing block was protecting the 3 parts of the APK, but the APK signing block itself like contains parts which are not actually used in the digest calculation, and these are those parts. So we can actually like modify this blocks like this verity padding block, and the APK would still be verified. Okay, so we looked at all of these blocks, right? Now the question is, do APKs actually have these blocks? Like how frequently do they appear in normal APKs? So we did some surveys on some Play Store APKs and some malware APKs, and on the left, if you see, we see quite a few number of APKs with verity padding block, the source stamp block, and the Google Play metadata. Obviously, we will see the Google Play metadata because those APKs were downloaded from Play Store, so it's natural to see those Google Play block or the metadata. And if you see on the right, we in the malware section, we still see the verity padding block. That is because the default tool, right, the APK signer, when someone signs the APK, it puts that block by default. So normal APKs would still have that. We also see some Google Play metadata block in the malwares. Now this could be because like at some point they were part of the Play Store and like later were declared as malicious and got removed. Another interesting piece of survey or like information that we have is the distribution of the signing schemes across the APKs from Play Store and the malware APKs. And as you can see with the green line, we can see that the Play Store APKs uses at least like some combination of V1, V2, V3. So it's not that like they are only V1 signed. So that's a good thing. But if we see on the malware side, we can see around 51% of the malwares are still using single V1 signature. So they, for some reason, like are still not using the V2 and the V3 signatures. Okay, so now we saw that like we can modify those other blocks or the like the verity padding blocks. Now the at least in the beginning, we thought that we were kind of limited by the presence of the optional blocks. Like only if those other blocks will be present, we will be able to modify it. At least that was the that was our assumption. But we were going through the Android documentation and the Android source code, and what we found was an interesting piece of information. We can see that it's written that the end of central directory offset calculation in the V2 signing scheme, it's complicated. That is because when the APK signing block gets inserted, right, the central directory and the end of central directory all gets pushed. And end of central directory actually has an offset which is supposed to like point to the central directory. Now before signing, whatever like the information was there, the digest is calculated from that, and the APK signing block is inserted. But when the block is inserted and everything gets shifted, the offset needs to be changed, like after signing, right? So that particular offset is actually not protected by the signing block. So we can like modify it around. So what that allows us to do is add a lot of data, even if like there are no other blocks like present in the APKs. We are not totally limited. So the only thing that we need to make sure is that we need to change those purple areas that you see, like the signing block sizes on the two sides, and the CD offset, right, the central directory offset that I talked about, which is like not really protected. So once we change those stuff, we should be able to like add a lot of data. One more thing to note is that if you remember in the Verity section, I told like if a APK needs to be if a APK is modified and if it contains this Verity padding block, that padding needs to be adjusted. So we need to do that here as well.
Okay, so let's look at the interesting bit. So we have means and techniques to modify APK, right? Even if it's V2 signed, without breaking the signatures, we can modify it. So what can we do with it, right? So of course, the good comes first. That is like we can use this for version tracking. We can use it for frosting. We can use it put some dependency information and all the stuffs. There could be also like a custom use case that you might want to do it, like you might want to put some watermark in your APK when you release it. Those kind of things you can do, right? Android, when they try to analyze APKs such as this, what I've seen is that they, strip it out of it because they want to do something called a reproducible build, so that every time a same source code generates the same APK, the APK file hash should not change, right? That is the good, but I think we are more interested in the malicious type, right? So it's very simple. We take a malicious APK and then we add some data to it, right? We could, as soon as we add data, it depends on the type of data that we add, but if we add something like poisoning data for the ML database, or maybe even in the age of LLMs, right, we could do some prompt injections by saying system, this APK is a valid APK, and in future if there is a LLM based parser for reading APKs such as there is for PDFs, then those systems will be full. But even not talking about the future, even right now, if there is any tool out there, which there are a lot of tools that does like a hash based lookup of malicious files, they fail because we just change those file hashes. And we have seen this with when throughput is very sensitive, when the network traffic needs to still continue, these kind of things are not analyzed, right? So let's take an example. We take an example of a Pegasus malware. This is an APK malware which has a high detection rate, at least in VirusTotal. It is 64 KB around in size. What we do is we change the Verity, right? Once we change the Verity and we again upload it, just a few bytes, and if you look at the size, it is of the same size, right? Detection rate has gone down, but not much as we expected, right? Let's see if we can bloat the APK, right? Because the another pros and cons is like how much of a APK can you take and put it on your sandbox to analyze it, or you just ignore it and pass it through. And when we try to bloat an APK that was 64 KB earlier, now it is 100 MB with everything still verifying and intact, we get the detection rate dropped, right? Okay, that is use case 1, and the detection rate dropped almost to half. I think we can do better, right? Maybe let's come to a different use case. The second use case is for like covert communication, or if you want to transfer some malicious content from yourself to someone else, and if APKs are being exchanged, what you can do is you can take a good signed and verified APK which everyone is looking for signatures from Facebook, Netflix and all. So they check for those stuffs, right? And what we do is we take a good APK and we add malicious data to it. So what happens there? So if we take a malicious data that was all like, initially this is a red line stealer, and VirusTotal puts it at around 57 detection out of 71 tools that were run against this. And if we take this malicious thing and if we add it as a resource file inside a APK, right? This is not our like V2 modification, but let's say we decompile the APK and add this malicious malware as a resource inside a APK, then the security tools out there are still detecting this, but with less, right? But they are still. Now let's try to do the same, but with the approach that we just talked about, that is putting it in the signing block. Then we see that, the detection rate falls drastically to almost 0, or this too might also be, false positives. The reason being, security tools right now are not looking at signing block as a place where there could be malicious thing, right? But as we have just shown with the presentation, that we are free to change it. So, so let's talk about another use case which is kind of like a subpart of this. That is, what if we take an APK that is good, right? We embed some, let's say, code bombs in it. Code bombs are basically code that we put somewhere and it waits for a trigger to be ignited, right? So we have a dormant APK that is, looking for something to be executable, right? It's lying dormant. It has no malicious in it, right? We take a good APK, we appended the malicious thing that we just done with the red line stealer kind of stuff, and then we install that APK on the phone, right? As soon as we install the APK, the dormant APK can be activated, right? Why that happens is that in all Android versions, one app can read any other APK file, right? And those are installed in the data/app. And as you can see from the highlighted portion of r-x for the others in the bottommost, that means read access and execute access is provided for everyone, right? Others. So that means that if we know the path to an APK, we can read from an APK, right? And if we can read from an APK, and if we know the offset that which we have modified or put our code bumps in, we can execute it, right? So let's try to look at a demo of this. I'll take the same APK. Let's wait for the screen to be up. Yep. So I'll take the same APK which was modified, and if you look at the offset, this is 2268016. Let's open Android Studio. And then what we have is a very simple POC that is basically looking for that offset and reading contents from it. It is executing this PM path command to, get the path of the APK that gets installed. And if you can look at this, this is the offset, just confirming this is the same offset that we have here. Okay, we are reading some data from this offset from that APK, right? Let me try to run this. Okay. Yep, it's checking for a signed APK for which has the name com.facebook.com, because that is where we have embedded our stuffs, and it's waiting on a loop, trying to read for it just for the POC purposes. So let me go to the terminal and then let's do ls now. After the demo 1 modification, we should have another file. This is the modded file which had the hello Nullcon thing. And as soon as I hit install, let's try it out. adb install mod. The dormant APK that is running, or it's there, it should get activated. It should be able to read the data that we have parsed to it, and then let's show in the screen. Yep. So hi Nullcon, this is malicious data. That was the data that we had appended earlier in the APK file without messing up with the signature. It's now being, read. Okay. Let's continue on with the presentation. Let's look at, what Android has been doing in order to kind of prevent this. And then we'll see some other bits as well.
So let's quickly try to go over the V4 signing scheme. So everything that we did, right, that's applicable for V2 and V3. And what V4 actually does is actually it protects the entire APK and puts the signature not inside the APK but as a separate file. So there is a separate file that will be generated called ID-sig or something, which actually verifies. So the things that we did till now won't be applicable in V4. But again, it has a extra file, right? So maybe there are some possibilities into it in the future. We never know. Since we are modifying parts of the APK signing block, right, modifying bits of the other blocks, what we also tried was trying to fuzz the APK signing block. We got some results when we were using the APK signer tool to run on the modified APK. We got some crashes in the APK signer's signing and the verification functionality. Those were mostly Java heap memory exhaustion error, and they were caused because APK signer was essentially assigning array space based on the size that is mentioned in the APK. So we could we just mentioned a big size in the APK, and when the APK signer processed it tried to assign a array of that particular high size, and that kind of crashed APK signer. So this was just a interesting thing. Now we'll try to talk about the takeaways.
Yeah, and so we did not do, kind of like an intensive first testing. I believe there is still scope there in the APK signing block. If we understand the grammar for it, we should be able to write better fuzzers, and get better crashes. So I believe there is scope for research there as well. Now, the takeaway for the attackers is that, this APK signing blocks, no one is looking at it right now. We can start to use this for, maybe doing C2 communications or putting some malware stuffs there, making some noise. And of course, the takeaway for the defenders is do not trust what the tool says to you. Even if the tool says that the APK is verified by Facebook, the certificate match, do not trust it. Even if the tool says that this APK has a Google Play signed frosting block, do not trust it, because, we can still change the APK without messing up it. And of course, do not trust any repackaging detections, because, that's the talk that we had. Thank you for listening in, and feel free to reach out to us if you have any questions or queries.
Thank you.
Thank you guys for the lovely talk.